Hi students. Now in Doppler effect, there are some special cases. In the previous case one, we have just now explained what will be the apparent frequency when both the source and the observer are at rest. So there is no change in the frequency. Now case 2 and 3 can be studied together. So what is case 2? Observer approaches a stationary source. So in this picture I have taken the source is on the left hand side. Now it is at rest. So what is the symbol Vs denote? Velocity of the source. It is still at rest. Imagine a train is at rest on the track. It is now whistling. But an approacher is coming from the end of the platform towards the train. So when he is moving towards the train, he will listen a frequency greater than the actual frequency. That is the case we are going to discuss. So observer is moving towards the stationary source. So observer is moving with the velocity VO. Here VO is not equal to 0. And the sound is now coming from left to right along the positive x direction with the velocity V. And the observer is going from the right towards the left with the velocity VO. So sound and the observer, the sound waves and the observer both are moving in the opposite direction. Only the source is at rest. Okay. So there is a relative motion. There is a relative motion between the source and the observer. So the actual velocity of the sound is V, and there will be relative velocity of the sound with respect to the observer. So what is the relative velocity of the sound? So relative velocity of the sound or waves, any waves, light, maybe light waves also, same concept. So in this case I have taken the source of sound. So what is the relative velocity of the sound? V relative velocity, VR, is equal to V plus VO. This is the relative velocity. Understand that? But in this case, still the source is at rest, is it not? It is continuously emitting the waves, that's all. But the wavelength will be lambda still the same, because the distance between the two consecutive compressions or rarefactions will be the same. So the wavelength is not going to change, it remains the same. So here the apparent frequency is given by f dash. F dash is equal to this relative velocity by wavelength lambda. So in place of relative velocity we can write V plus V observer divided by the wavelength lambda. So this is equation 1. So the concept is, here the wavelength is not changing, okay, only the frequency is going to change. How? Let us discuss now. Now the actual wavelength is represented by lambda, and the actual frequency which is emitted by the source, this actual frequency is given by f, and this is equal to V divided by lambda. This is equation 2. In the first case, previous case we have studied, is it not? The actual frequency is the number of waves emitted by the source. So that is F. That is equal to the actual velocity of the sound divided by the actual wavelength. So in this case I can write lambda is also equal to what? Lambda is equal to V by F. So I can write here, okay, or lambda is also equal to V by F from this equation 2. That I am going to substitute for lambda in equation 1. Okay, therefore now f dash is equal to, so f dash is equal to V plus VO divided by, in place of lambda I can substitute V by F, so that this is V by F. The numerator factor f can be brought to the numerator here, is it not? See, this is actually in the denominator, but when it is shifted up, it will come to the numerator. Therefore, f dash is also now equal to this f multiplied by V plus VO divided by V, and this is equation 3. Okay, now look at the numerator inside the bracket. It is V plus VO, and denominator is only V. So the numerator is greater than the denominator, isn't it? So the value of f dash must be greater than f. Therefore, in this case, f dash is greater than f. So this is why we feel as if there is increase in the pitch or frequency of the sound when we move towards a source, understand, which is at rest. Now to understand this, a very simple example, very simple example, let us take. Suppose if a train with some 25 compartments is moving on a railway line, okay, on a railway track. You just stand at one place. And count the number of wagons crossing you in 10 seconds. So one after the other, the coaches are crossing you. Where you are standing, it is crossing you. Suppose some 15 coaches have crossed you because you are at rest. Next, the same is observed when you are moving in the opposite direction. So train is going in the x direction, you are going in the opposite, that is minus x direction. So in this case, for the same time of 10 seconds, definitely you should have counted more than 15 coaches. Am I right? Practically you think. So like that, the number of waves crossing the observer per second will be different when he is at rest and when he is in motion. So when the observer is moving towards a stationary source, he will definitely listen to more number of waves per second. That is why there is an apparent increase in the frequency when he is moving towards the stationary source. That is why here the apparent frequency is greater than the actual frequency. Understand? So this equation is very important. So in all the cases which we are going to discuss, I have considered the medium, air, through which the waves are traveling. That is at rest. I have considered the medium is at rest. So the velocity of the medium is assumed to be 0 for the derivations. So in this case, apparent frequency f dash is equal to actual frequency f multiplied by V plus VO divided by V. Understand? So f dash is greater than f, where the observer approaches a stationary source. Okay, his velocity is opposite to that of the velocity of sound. Now we are going to consider the case 3, where the observer recedes away from a stationary source. Receding means this observer is moving away from the source. He is moving away from the source means the observer is moving along the positive x direction. Understand? So in this case, naturally there should be a decrease in the frequency. So here only one change, that is velocity of the observer is opposite direction. So it is taken as minus VO. So in this case, okay, here V observer is negative. So it has to be substituted as what? Minus VO. So in the equation number 3, instead of VO, minus VO we have to substitute because he is now moving away from the source. Therefore, here the apparent frequency f dash must be equal to f into V minus VO divided by V, and this is equation 4. So you can see very clearly the numerator is V minus VO must be definitely less than V, isn't it? Therefore, f dash, okay, f dash must be less than f. This is why when you go away from a stationary source, a whistling train for example, okay, continuously train is whistling and you are going away from the train by listening to the sound means as you go away, the sound frequency appears to decrease. Understand? So, my dear students, you have to remember that when the observer approaches a stationary source, the apparent frequency increases. When the observer recedes away, moves away from a stationary source, the apparent frequency decreases. I hope you must have understood the fine.